Okay, let's do 3 more examples from here of solving equations. And these all 3 have a little bit of a, I'm going to use the word twist, maybe, a little extra thoughts that we have to use relative to what we've done on the other ones. Maybe I have tangent squared x plus tangent x minus 12 equals 0. Okay, now notice all of these, all but maybe the first one that I did, were already set equal to 0. And so again, if they're not and you see that tangent squared or that sine squared, you're going to want to get a 0 on one side first. I think the author has most of them already in that form. And you say, Ms. Jackson, this isn't any different. I can factor that, just like we factored the 3 others that we just did. Because I know the numbers that multiply to be negative 12 and add to be positive 1 are positive 4 and negative 3. And I know how to set each of these factors equal to 0. And I know how to solve for x. The difference here on this one, and this could show up with a sine or a cosine, it's nothing special about the tangent, but there is no special angle. It's not one of our pi over 6s, or pi over 3, or pi over 4, or a quadrant angle where the tangent is equal to negative 4. And so where we ended the last chapter is we were working with inverse functions, and so I know that all I have to do is take the arctan of both sides, however you like to write that. And we can push those buttons in our calculator, which I did not bring to class, and so you could get a decimal value out of that. Read the directions. If the author asks you to solve these and round to the nearest whatever, please go ahead and do that. But also we have to take into consideration if we are finding all of the solutions. Okay? And again, in some of the sections the author says only give me the ones between 0 and 2 pi. And if that's the case, then all we would have given back here would have been the 7 pi over 6, 11 pi over 6, and 3 pi over 2. Okay? If it just says solve for x, we have to give the whole spectrum, all of the infinite solutions. Okay? Now we have to take the period into account, and with the sine and cosine, and therefore secant and cosecant, those periods were all 2 pi. But think for a minute about the period of tangent. Okay, the period of tangent is just plain old regular pi. So our set of solutions, okay, would be arctan of negative 4 plus the multiples of pi, integer multiples, not the 2 pi's. Okay, and arctan of 3 plus n times pi. Okay, there's our infinite number of solutions. If you land on an equation where it's not something nice and neat like 7 pi over 6, or like 3 pi over 2, or like plain old regular pi, okay? Or back before, some of the same ones over and over again, pi over 3 and 2 pi over 3. Okay, then we get to use our inverse trig functions, and the best we can say, again, we can push those buttons on our calculator. Make sure you're in radians, please. Okay, and give me the decimal plus n pi, okay, or in all fairness, I would accept arctan 3 plus n pi, if you want to leave it that way. So maybe I have 2 sine squared x plus cosine x minus 2 equals 0. And when I look at that, it's sort of like a quadratic equation, but it's really not at all, because I've got 2 different variables, quote unquote variables there. I've got part of the equation in sines and part of it in cosines. So you've been wondering, I'm sure, when are we going to use that stuff we just finished with all the identities? And it doesn't happen in every problem, but there are some problems where we get to use those. Okay, so if I have a mixture of sines and cosines, if I have a mixture of secants and tangents, or sines and secants, or whatever the combination happens to be, before I can approach the problem and actually try to find solutions, I have to be able to write them in terms of only one of those functions. Okay? So I either have to write my cosine x as a sine x, or I have to write the sine squared x as a cosine x. So if we think back to those identities for a moment, pause the video if you need to not have me jabbering in your ear. Okay, please do that at any time if you say, I got to think about this before you say it, Ms. Jackson. Shut the video off and think your way through it, and then turn it on to see if you're on the right path. Okay, those Pythagorean identities are going to be, I'm going to say, going to be your best friend. We are going to, I think in the next section, maybe 2 on down the road, add a whole bunch more identities to our list. And don't panic because, don't panic please. Okay, so if I have a sine squared x, or if I have a secant squared x, or if I have a cotangent squared x, then I'm always thinking, is there a Pythagorean identity I can use for this? And sine squared of an angle is 1 minus cosine squared of that angle. So 1 minus, that says cosine squared x. Okay, so I can distribute the 2 to both terms. Then I can combine my like terms. And then I say, oh, this is really just a quadratic equation. Quadratic-like equation. I'm kind of sloppy in my verbiage there. But I have minus 2 cosine squared x plus cosine x, and then look what happens to the 2's. Okay, in this case they're all gone, but maybe they wouldn't be. Maybe I'd have a trinomial looking thing in another problem. Okay, when there are only 2 terms instead of 3, and when there's that squared term in there, some students panic for a moment. Okay, but just always remember, can I factor this? That's your first thought, can I factor this? And so if I look at this expression on the left side, sure enough I can. I can take out a greatest common factor. That should always be where I start with anything I'm ever factoring ever. I'm going to personally pull out the negative sign with the cosine x, but there's no rule that says you have to. You could leave it in here in the parentheses instead. But I'll have 2 cosine x minus 1 now. Once I have it factored, I set the factors to 0, then I solve each one for x. Okay, again, if you want to pause right here, it's a great place to pause, and then you can work them all out, and then compare your answers with mine, because I'm going to just keep rolling here in a moment. We know the cosine function with or without that negative sign. Cosine is 0 or negative 0, okay, which is still 0. The cosine function is 0 at pi over 2 and at 3 pi over 2. Okay, top and bottom. Okay. The period of the cosine function is 2 pi. Again, you can put your n at the end. That's what I did on the other page. I put it in the middle here. But you need the 2 and the pi and the n there. The other one says cosine x equals positive 1/2. And we know the cosine function is positive in the first quadrant. That's pi over 3. And think for a moment what other quadrant the cosine is positive in. First and fourth. So 5 pi over 3 would be the fourth quadrant answer there. Hang on just a moment. Okay, I copied the problem wrong out of my book, but we are still right for what we have written on the board, just not for what I had in my notes. Okay. Because the period of the cosine function is 2 pi, then we have to add our 2 in pi to that. And so here's our infinite number of solutions from one piece, and the other infinite number of solutions from the other piece. And there's not really a good way to combine them together into one single batch. I mean, that's all the mess that we're left with. So if you're given a function that has more than one function in it, sines and cosines, secants and tangents, cosecants and cotangents, usually it's those pairs. Hopefully you've got a Pythagorean identity you can work with to turn one into the other. Okay, and if all else fails, go sines and cosines and see what you're left with. Let's go back down the linear path for a minute and say we have sine of 2x plus square root of 3 equals 0. So my sine is to the first power, like it was in the very first video from this section. But the difference here is that I don't have a plain old x, okay, in my video, in my problem. And I just noticed how long this video is getting, so I'm gonna stop it here, and I'm gonna start with this problem in the next segment. Okay.